So today I will talk about our journey to functional safety with Rust. So we'll talk about what is ADAR, what were our technical challenges, where are we today, and what are the next steps for us. So what is ADAR? Well, you can see it here. I have a prop here, so you can take a look. This is a mechanical demo, so take a look at it, send it around. It is an ultrasound 3D sensor. It emits an omnidirectional ultrasound pulse out into the air. Then the sound comes back, the sound is recorded on multiple transducers, and then we have custom algorithms that analyze the recorded sound and produce a point cloud from this. And then the output is on these wires here. Well, you can't see them, I don't want to lift them in case I break my demo, but basically it's a yes-no system, right? Can I keep going, or do I need to stop? The technology, that's a Lego figure that you see there. His hand is this small. It's a MEMS device, that's a transducer. We have shrunk the transducers that you have on your parking sensors to very, very, very tiny. And that's what emits the sound. And we call it ADAR, Acoustic Detection and Ranging. So it's our MEMS, and then there's the signal processing, and then we're now adding the safety on top of that. So we emit this, you see the ADAR down there at the right, and it comes out, and then it hits the person, and sound comes back, and that's what we detect. And then we define a safety zone, number of protective zones or warning zones around the robot that we want to protect. It could be in front of an AMR, an autonomous mobile robot. It could be around a static robot that we want to stop if someone enters the system. And of course, also humanoids are getting interesting. So we have the stop zone and the warning zones. Turns out that our customers need not one setup, they need not two. We actually have a very clear indication that they need more than 64 different zones, because it's the turning right zone, it's the getting around the fridge zone. It's crazy. But that's what they need, or that's what we think they need, so we made it. So what we're doing, we're bringing safe 3D sensing to robots. And why is this useful? I mean, this has been solved already. All the robots are out there, they're safety certified, but how did they do it? They do it with 2D LiDARs, and they are great. I mean, LiDARs are awesome. But if you see these green sections here, that's what the LiDAR says, right? It's excellent in the plane, but anything below it or above it is invisible. We send out a spherical wave, and that hits everything, and we cover then a 3D. And all sensors have challenges. We have ours, but we don't care about dust, light, stuff like that. Shiny surfaces, glass, big problem. A lot of LiDARs struggle to get through elevators and metal, right? Because it's just too much reflection. For us, that would not be a problem. So building into the diversity of the different sensors. So let me talk a bit about our technical challenges. So first, some physics. I mean, robots want to move fast. Now, fast is not super fast like a car, but definitely the faster they can go, the more they can do. And sound is relatively slow, 340 meters per second, versus sound, versus light, which is what's driving the LiDARs, 300 million meters per second. And 5 meters is a range that we want to be able to detect stuff on. Sound has to go there, come back. That's 10 meters. That takes about 30 milliseconds. And what we hear from the field is that they need to know if there's something there within 100 milliseconds. The problem is that the object can enter at the worst possible timing, so we need to divide those 100 milliseconds by 2. So that gives us a 50 millisecond heart rate. By time we need to know if we need to stop in order to tell the system whether it needs to stop within 100 milliseconds. So time of sound, 29.4 milliseconds. That leaves us 20.6 milliseconds to do the compute, which is not a lot, because our algorithms are complicated. There's no way to complete them in 20 milliseconds. So obvious solution, we start to process as soon as the first sound arrives. And this cuts the start of processing from 30 milliseconds to about 3 milliseconds, leaving us a comfortable 47 milliseconds to do the processing. Yeah. Turns out that analyzing the sound that arrives and converting it into a point cloud is really hard. Luckily, we have some pretty awesome experts on the team, one in the audience here as well. And so we applied our team's experience from medical ultrasound to our domain. But it still requires a lot of compute. So we started 3 years ago. So the first prototype, classical startup, see all the wires. It's actually a plank, it's wood. But it served a purpose to get us started. Second platform, got a big round thing there is like this, and each board has its personality, so they actually got names. Yeah. But for this one, we knew that we were going to need to develop algorithms. We knew that we would go embedded. And we had heard about Rust, and we knew that the ST series were good ADCs. So we decided to drive all the firmware on side there in Rust. Kind of as an experiment, and kind of because we thought it made sense. But back at that point, this was a leap of faith. I considered the certification risk quite large at that point. Processing was done in Python and MATLAB on the PC. And then we created the evaluation kit, which is here, which we shipped out to a number of customers. And here we moved the processing inside the chip. We still cheated. Still got the H7 doing the transmission of the sound and the digitization. But this is actually a Raspberry Pi running Linux. But we did port all our algorithms from Python MATLAB to Rust. So here all the algorithms are running in Linux. So that means already at this point, we were developing our algorithms in the language and benchmarking them in a way that we knew we could put onto the device itself. But there was not enough compute power. Or sorry, the Raspberry Pi had enough compute power, but not very certifiable, right? It runs Linux, and yeah, not certifiable. So we had to come up with a new platform. So we went hunting for a hardware platform. So first idea, okay, can we get this into this H7 that we now had some experience with, comes with a dual core, with an M4 and an M7. Could we do make the M4 the analog front-end thingy and do the processing on the M7? Yeah, that could have been a product. But with the requirements that we had, it would not be fast enough. So second attempt was, okay, we liked the H7. We had experience with it. It was good Rust support. Yeah. So a triple H7. So still an H7 in front, and then two H7s, and then we need some glue too. But yeah, still not fast enough. So we went hunting, and then we found this beast. Yeah. This is this is actually a snip from the Confluence page where we did our benchmarks, and you see we call it Computing Monster. That's what we called it. It has a quad-core A53. No Rust support, but it does have bare metal support, and it is designed for functional safety. And it has an MCU, an M4 up there in the corner or in the center there, that is got lots of extra features for safety. So this looked like a good fit. But we need to run our code on this thing. So obviously the easy solution would be with Linux. I mean, this comes with Linux, just boot it up. So the first thing we did was just actually take our Raspberry Pi code, put it onto the Linux here, and we could actually run it. We needed to do something to get the data in, but we could actually run our algorithms on it, so we could benchmark it with that Linux. But not certifiable on Linux. So then we looked at ThreadX. We got some recommendations on that, which looked quite promising. We were really leaning towards that until we realized that, well, ThreadX, you get the operating system certified, But you still have to do all the low-level assembly code, doing the dirty deed of switching between tasks and all that stuff. And I'm sure that's doable. I mean, people do it. But we did not want to have that responsibility. It was too much work, and we don't need a full-time operating system. So then we went out and see, okay, are there someone out there who can port a certified OS for us? Because there was no OS for this target, of course. And there were, but they needed a lot of money. And we are a startup. So that was absolutely too many zeros on those numbers that they gave us, which led us to think, oh, okay, if they know what they're doing, and they say it costs this much, okay, what are we getting into here? So obviously we did the crazy choice, and we concluded, well, let's run this beast on bare metal. We do the heavy lifting. So I just said no to the assembly, now I'm saying I'm doing the assembly. Well, the thing is, we have a very, very trivial, from an operating point of view, we have a main function that just runs. So we don't need all that extra stuff. That's why we thought at that point that this was a good idea. And we had checked that the TI chip did have C code that could run. So we had already established that we were able to compile the C code, get it running on the evaluation kit, and we also compiled the Rust code and saw that, okay, we can get something running here. But where did the support go? So on SDA, there's low-level support for the Cortex-M. There's a PAC, there's a peripheral access crate, there's a hardware abstraction layer, there's ProBAR-S support, there's deformat. For the TI chip, yeah. Well, OpenOCD works. Or we got OpenOCD to work. Thank you. So no Rust support, no PAC crate. The reference manual for that monster is 15,863 pages long. It actually has problems opening in Linux, so we actually created a dump that does not export the last 1,000 or 10,000 pages in order to be able to work with it. And at the time we started, there was no embedded HAL for A53. And they do not provide SVD files. They do provide XML files. And Endre found a crate that can convert the XML to SVD, and then we put that back into SVD to Rust. And then we have 30 megabytes of generated code. That's just to get to the peripherals. That's 30 megabytes of Rust code. So let's do something with this. So luckily, our problem is well suited for parallelization. So it's 3 phases. It's the data recording and pre-processing phase, and there's the analysis phase, and there's the conclusion phase. And it's the analysis phase that is compute intensive, and it's ideally, performance can be achieved by divide and conquer. So we can hand out the tasks. So we have a quad core, let's make the course work. So independent tasks, task execution time is not constant, but it is deterministic. And then we use atomic counters as the only synchronization mechanism between the cores. The cores are running on a quad core, so we do have some help from the hardware in terms of the L2 cache is shared. So we can communicate, even though the data lies on the external RAM. So data, of course, arrives over a serial bus with DMA. So miraculously appears in RAM, which of course is a bit contradicting to Rust idioms, so hence unsafe several places. But we know when it comes, and then we increment a there is something to do counter, an atomic counter. And then the other cores say, oh, is there something for me to do? Yeah, there is. Picks one atomically, and then once it's done, it increments the yeah, I've done it counter. So that's how we hand out the data. So core 0 is giving the special responsibilities for doing all the peripheral work, for doing DMA, sending requests over to the analog front end, stuff like that, and then increments the write index on arrival of new data. And then the cores 1, 2, and 3 are just stuck in an active loop, basically looking for whether the read index is larger than the write index. And this is our scheduler. So we check, is there something to do? Is the write index, is there how much data is in RAM? And then we check the read index. We increment it if there was something to do. And if there was something to do, we apply this function, this f, that is a function pointer to do work that takes the raw data and converts it into what we need it to be. And then it increments the done count at the end. And hence we get a non-blocking, multi-core, bare metal implementation with no locks, no mutexes, only atomics. So we recently were able to move some code that was running on one of the cores out from the A53 and into another core. And that more or less gave us exactly a one-to-one increase in performance because we got one more core to do, because there's almost no overhead with adding cores here. So, compute challenge solved. So we start processing while samples arrive, multi-core blocking. But wait. We need functional safety on this thing, because this 3D problem that we're solving, well, it's kind of also solved with cameras, right? Cameras and AI also do a really great job on object detection in 3D. They don't have our field of view, but they have, I mean, it's impressive what they can do with cameras and AI. So getting the safety on this is critical. So at this point, Rust compiler was out, Ferrocene had delivered. So when we started, it was a bit leap of faith. There were promises that they would. At this point, they had. Great, we can do this. Wait, libcore isn't. So I have a compiler, and I'm going to write code, but I can't use libcore. Okay. So some frantic discussions, and then we called Ferris, and we talked, and they have certified a subset of libcore. Just, I don't know if you got the certificate yet, but it's handed in.
Very close.
Yeah, very close. Close enough. And
enough that we made an announcement about it.
Exactly. But that's a subset. And so it's not all of libcore. But wait up. What about our fantastic monster? Not safety certified, but it is designed for safety. It has this M4 and the quad-core A53. It actually also has an R5 running here down in device manager there. So the normal case for this kind of chip, and this is an automotive chip, right? So you guys in automotive have seen similar things. But the normal case is you have your safety function in the M4 or in a lockstep R5 thingy. And then you have your entertainment system or something running on the A53s. Of course, we chose the A53s because that's where we need our safety function. So what we do is we run the safety function on the A53s, 100% Rust. Then we run the integrity function on the M4. So the integrity function, for those of you who don't work with functional safety, that's the part that sort of checks that everything is running okay. So it's a very nice separation of concern. It also gives us, and it's a core where we can do this. And then we have the non-safety part of the system running on the R5. So that's where we running the communication, because the Ethernet communication is not part of the safety system. And that's unfortunately still C. I mean, and they really wanted to port the FreeRTOS and the network stack to Rust, but it's kind of working. Except that's the one place where we have a stability issue. It's in that black part. So, yeah, we'll see what happens. But with this setup, we need to, and especially since we do have this evil FreeRTOS running that can do anything, we need to prove that we have freedom from interference. And we have the MMUs and the MPUs on the separate chips, but we can't really trust them since FreeRTOS then configures the MMU, while it could unconfigure it. Luckily, the chip also has a firewall. Also has a firewall. that we can use as a second layer. And with that, we are good. As I said, there's a lot of mathematics going on in here. So we know that this is heavily optimized with the SEMSys DSP. So our assumption was that we have to use that, and we have to come up with evidence that our usage of SEMSys DSP is safe and correct. But then we came across the Rust FFT crate, and we benchmarked it, and it turns out it's actually faster than the SEMSys DSP. To be fair, faster in terms of faster for us. So, I mean, it might be that SEMSys DSP is actually faster, but because we're passing through some FFI boundaries, so I don't know, but I don't care. Rust FFT was faster. And then my colleague, he was like, FFTs, that's been done quite a few times. What if I give one of these AIs the task to write an FFT? And he did that, and he spent like a couple of hours on it, and we got a native Rust implementation from AI. It's actually faster than both the Rust FFT and the other one, so it's worth to give it a try. I mean, for sure, FFTs are probably one of the better trained models, but still, we thought that was pretty cool. Today, ADAR 1.0 is shipping, not safety certified, but functional. Evaluation is ongoing at many customers, and we have one customer who's designing in, so we expect to see it actually in robots early next year. Here we have the prototype out in testing. But enough talk, let me show you. There we go. So what you see here is a great tool called Foxglove. It is a visualization tool for point clouds. And what you see, does my mouse work? No. So you see the black box, that's a sensor. So you're sort of seeing the 3D view here, you're looking out like this. And this one, you're looking top down. And the boxes are the safety zones. So if I walk here, you can see me. And there, I entered the outer warning zone. And then I entered the inner warning zone. And then, well, I made a very small zones because I didn't know how big how this would work. And it's 3D, so I can go like this. The zone is about 40 centimeters up, so I can go like that. And then at some point, I'm inside. And I made all the zones the same height. That's why all of them went on. So that's it. So ADAR 1.0 is more or less feature complete. We are now switching focus to getting the safety certification. So we're working together with Exida for that. Process documents are being reviewed and approved, and we have an FME day that, well, it's not approved, but like you said, we're close. Ferrocene is available for our targets. LibCore subset is getting certified. And yesterday I played around with the certified targets from Ferris. So now I can compile against the ARM64 Ferrocene certified target. And not surprisingly, that does not compile because we are using non-certified code in our code base. But at least I can start playing around with it. And the plan is to give Ferris the list of LibCore features that we need for our product so that they can focus on getting those parts of LibCore certified in their next release, which is just in time for us because we want to release, we want to have safety certification in early next year. What they have done is that they've feature flagged LibCore. So they're only, if we compile with this, we only get the parts of LibCore that's certified. Now, for us, I mean, one of the reasons why we all love Rust is the crate system, right? The ability to pull packets in. And for us, for example, we use heapless. We would like to use this FFT thing, but typically you only use a very small subset. So we think this idea of letting the documentation be the specification and using that to provide evidence is interesting. So we're thinking this pattern could also work for third-party crates, and it's been a topic for several talks already. How do you get this back into upstream? How do you avoid forking? And then how do you keep on track with the upstream? Things like that. So there's definitely a lot of things to be said, but it would be nice if we don't have to just rewrite stuff that's already there just in order to make it prove that it's for safety. So of course, we have to limit the third-party users to absolutely the minimum that we have to. But we would rather lift the quality of the third-party crates we use than to rewrite it ourselves. And it would be nice if we as a community came up with some way where we could all share this. Because I don't care if you reuse my evidence. Probably that just improves the quality. I need to focus on my domain. And if I did some evidence that you can use, great. So to summarize, we have released ADAR, fully functional, not yet safety certified. We're switching gears right now to safety certification, and we plan to be safety certified by end of Q1.
We had a very eager hand go up here.
Yeah, I have a question for hardware certification, because you talked about software certification, but how do you certify that the chip you are running your code on is properly developed according to the certification requirements?
We don't trust it.
Okay.
So we have all these mechanisms to prove that we don't rely on the trust. So for the raw data, we transfer the raw data over SPI. We transfer the CRC checksum via UART. This whole integrity program is running on an M4 with a 30TP architecture without DSP. The actual computation is running on an A64 with Neon DSP. And. Yeah.
And back here.
Thank you very much for your talk. This was very interesting. When I look at the quality of the signal that you detect, and when I think about comparing this to what nature has come up with, maybe in bats, for example, where do you see currently the bottlenecks in the quality that you can produce? Is it more on the hardware level, like ultrasound transducers, detectors, or is it a compute? Or what kind of quality improvement would you expect if you could maybe quadruple your processing time?
There's many layers to that question. One of the things that it's very hard to find the right balance between seeing everything and seeing just the things that you care about, right? So what is the, because basically what this sees or it hears is, right, it's the strength of an echo, and depending on the shape of the object that you hit, you get very different amount of sound back, and so it's very hard to tune a filter that gives you the object that you want to stop for, but does not stop for a crack in the floor. So I think that's where the ultrasound challenges are the most, and then coexistence is also difficult. Yeah.
Okay, one last one.
Fantastic talk, by the way, and sorry, I just missed the first slide, so maybe the question is misplaced. Why sound and not light in the form of lasers in some way? Because light is way faster than sound.
Yeah, good question. Number one, we started because we had the transducer. That's the foundation of this company. So we have a transducer. What kind of cool problems can we solve with it? So that's one answer. And the other answer is that yes, light does solve many parts of this, but it's either very expensive or not certifiable. So the 3D LiDARs, they exist. They are either not certified or extremely expensive. Cameras, really good. AI, not certifiable. So, yeah.
Okay. Thank you, Espen, for that great talk and your demonstration. So thank you.